Hello, welcome to this class. In this class, we shall continue our discussion on ideal and real gases introduction. So, in the last class, we had derived an equation which is an ideal gas equation PV is equal to mRT. And remember, this is the equation which establishes a relationship between pressure, volume and temperature of a particular gas. Now, we have said P is pressure, V is volume, M is mass and R is characteristic gas constant, and temperature T is in absolute temperature, that is in Kelvin. So, we had tried to write the units: pressure in Newton per meter square, absolute pressure, V is in volume, that is meter cube, mass is in kg, R is a characteristic gas constant joule per kg Kelvin, and temperature must be in Kelvin. So, we will have meter square cancelling out. In left side we have an Newton meter, and kg cancels out. In the right side Kelvin cancels out, you will have joules. So, that is how your equation is balanced with the correct unit. So, let us call this PV is equal to mRT as equation 1. We can write the same equation PV is equal to mRT in different forms. This is where many students get confused. Now, pressure, let it be on the left side. I will send this mass to the left side. So, it becomes volume by mass. The same equation 1 I am rewriting. Mass I have sent it to the left side, it will go to the denominator. So, volume by mass, we know volume by mass is specific volume small v. The unit of specific volume is meter cube and mass is kg. So, specific volume is meter cube per kg. Specific volume. So, this can be rewritten as P small v is equal to RT. And again, it is important to balance the unit. Pressure is in Newton per meter square, specific volume is meter cube per kg, and we know R is in joule per kg Kelvin, characteristic gas constant, and temperature is in Kelvin. So, we will have joule per kg on the right side, and in the left side meter square goes off, and you will have Newton meter per kg, which is again joule per kg. So, equation is balanced. And very important, the same equation 1 can be rewritten in the form PV is equal to RT. So, this was our equation number 1. The same equation can also be rewritten in this form, PV is equal to RT, where this is small v, which is specific volume. Now, the same equation can be further rewritten like now before we move on to the next equation, do we know what is characteristic gas constant? Characteristic gas constant. Let us give a simple definition of characteristic gas constant. Now, characteristic gas constant is derived from R bar, which is universal gas constant divided by molecular weight. Now, these are all new terms which we will have to define. Now, R bar is universal gas constant. Universal gas constant. Same for all gases. Molecular weight, which is M, is molecular weight. Now, unit of R bar is joule per kg mole Kelvin, whereas molecular weights unit is kg per kg mole. Now, we will have to define many terms here. One is the value of R bar is 8314 joule per kg mole Kelvin, and molecular weight is kg per kg mole, and it depends on particular gas. So, we will see how molecular weight of particular gas can be taken from the data handbook. Okay. Now, what is a kg mole? What is a kg mole? Now, kg mole, it is very important, are sometimes referred to as kilomole or kmole, is simply number of particles. This has to be understood first. Kg mole is 6.023 into 10 power 26 particles. So, as good as like whenever we say dozens of egg, we always refer to 12 eggs. It simply is number, right? 2 dozens of egg means 24 eggs. Similarly, the moment I say kg mole, it is not related to mass, it simply related to number of particles. So, molecular weight can be understood now. If you have 6.023 into 10 power 26 particle, how much mass it is gonna weigh? Okay. So, that is what is molecular weight. Now, we have established a relationship between characteristic gas constant R with universal gas constant, which is R bar. Now, the value of R bar, we can derive it from Avogadros law. So, at constant temperature and pressure, the volume of gas is directly proportional to number of moles of gas, or we can say if you have equal volumes of gas, let us say this could be hydrogen, this could be oxygen. Okay. So, equal volumes of gas, so I have taken the same equal volume of gas. If this temperature and this pressure is equal to the temperature and pressure of oxygen, it will have equal number of molecules. This is true for all gases. So, equal volume of gases at same temperature and pressure contains equal number of molecules, or in other words we can say volume is proportional to number of molecules, or we can say that volume is proportional to number of molecules, or we can say V by N of one particular gas and V by N of other gas will be same. Okay. So, that is what Avogadros law talks about. Now, from the Avogadros law, now we have learnt PV is equal to MRT can be rewritten as in different forms. Now, let me take the same equation PV is equal to MRT and try to rewrite. So, pressure, there is volume, mass. Now, R can be rewritten as R bar by molecular weight M into T. Okay. Now, the total mass is number of kg moles multiplied by molecular weight. For example, this is in number of kg moles and molecular weights unit is kg per every kg mole. So, you will have mass in kg. So, this mass can be rewritten as N into capital M. So, mass is N into M, this R bar by M is here multiplied by T. So, mass goes off and you have one more equation PV is equal to MRT can be also written as PV is equal to N R bar T, and you can work on the units again. So, pressure is Newton per meter square, volume is meter cube, N is number of kg moles and unit of R bar we know joule per kg mole Kelvin and temperature is in Kelvin. So, kg mole goes up, Kelvin goes up, you have joules on the right side and left side meter square goes up, you have Newton meter which is joule. Okay. So, let us call this as equation 3. So, same equation is written in other form. There is one more way by which we can rewrite this equation. So, I will start with the same equation again. So, PV is equal to MRT. Okay. Now, P, I will send this mass here So volume by mass is equal to RT. Now this volume is specific volume now, volume by mass. Now R can be written as R bar by M into T. Now this molecular weight, I will send this to here, volume into molecular weight. Now R bar and T. Now what is this V into M? Let us try to derive the unit. Volume is meter cube per kg and molecular weight is kg per kg mole. Kg cancels out, you will have meter cube per kg mole. So meter cube per kg mole is something like, for every kg mole, that is 6.023 into 10 power 26 particles, what is the volume that particular gas is going to occupy. So this is called as molar volume. Now molar volume is denoted by the letter V bar. So V bar is equal to V into molecular weight. So P into this space, I will write it as V bar is equal to R bar T. Now this is one more equation, we can call this as equation 4. So P is in Newton per meter square, V bar is in meter cube per kg mole, and on the right side you have joule per kg mole Kelvin, temperature must be in Kelvin. So you have left side, right side joule per kg mole, left side also meter square goes off, you have Newton meter which is joule per kg mole is equal to joule per kg. So we have written PV is equal to MRT in different forms. Same ideal gas equation can be written in different forms. That is, we can start with PV is equal to MRT. Now if you send the volume that side, we will have PV is equal to RT. This is equation 1, this is equation 2 we have derived. Then so PV is equal to N R bar T, and at last we derived P V bar is equal to R bar T. So we have written same ideal gas equation in 4 different forms. So in the next class, we will try to cover few problems on these equations. Thank you.